You exist. And because you exist, things happen to you. Some of those things are predictable. Most aren't. And humans, being the anxious little creatures they are, decided that was unacceptable. So they invented a whole science dedicated to turning uncertainty into something slightly less terrifying. That's statistics. The art of making confident claims about things you're not entirely sure about, and somehow being right most of the time. Welcome to 4 years of a statistics degree. Let's go. Before you can analyze anything, you need to describe it. And before you can describe it, you need data. Data is just information. Numbers, categories, observations, your cousin's weird survey about favorite colors. All of it data comes in types. You've got quantitative data, things you can measure, height, income, how many seconds you hesitated before texting back. And you've got qualitative data, categories, eye color, country of birth, whether someone is a morning person or a liar. Within quantitative, you've got discrete data, countable things like number of children, number of failed attempts at parallel parking, and continuous data measurable on an infinite scale, like weight, temperature, time. Then there's the hierarchy of measurement scales. Nominal, just labels. Cat, dog, fish, no order. Ordinal, ranked, but gaps between ranks aren't meaningful. First place, second place, last place. You know who won, not by how much. Interval, equal gaps, but no true zero. Temperature in Celsius. 0 degrees doesn't mean no temperature. Ratio, equal gaps, true zero, the full package. Height, weight, income. 0 means nothing. Literally nothing. Why does this matter? Because the type of data determines every single thing you're allowed to do with it. Use the wrong tool on the wrong data type, and congratulations, your entire analysis is decorative. Now you have data. Time to summarize it. That's descriptive statistics. The goal is to take a pile of numbers and say something useful about it without listing every number. Because listing every number is what databases are for, not insights, measures of central tendency. Where does the data cluster? The mean. Add everything up. Divide by how many things there are. Simple. Elegant. Also, catastrophically sensitive to outliers. One billionaire walks into a bar, and the average income of the room becomes misleading. That's the mean. The median. Line everything up in order. Pick the middle one. Doesn't care about the billionaire. Robust. Used whenever data is skewed. The mode most frequent value. Useful for categories. Largely ignored by statistics professors after week 2. Measures of spread. How scattered is the data? Range. Biggest minus smallest. Tells you the total width. Tells you nothing else. Variance. Average of squared distances from the mean. You square the distances because some are negative and you don't want them canceling each other out. Squaring fixes that. Also makes the units weird. If you're measuring meters, variance is in meters squared, which is why nobody actually uses variance for reporting standard deviation, square root of variance. Units are back to normal. This is the one people actually use. It tells you, on average, how far each data point sits from the mean. Small standard deviation, data is tight. Large standard deviation, data is all over the place. Then there's the 5-number summary. Minimum, Q1, median, Q3, maximum. From this you get the interquartile range, Q3 minus Q1, which is the spread of the middle 50% of data. Resistant to outliers, beloved by box plots everywhere. Speaking of visualization, you'll spend a significant portion of your degree making and interpreting charts. Histograms for continuous data, bar charts for categories, box plots for distributions, scatter plots for relationships between two variables, pie charts for people who want to be mildly annoying at presentations. The shape of a distribution matters enormously. Is it symmetric? Is it skewed right? Long tail stretching toward high values? Mean pulled above median? Skewed left, tail dragging toward low values? Is it unimodal, 1 peak, bimodal, 2 peaks? The shape tells a story before you run a single test. Descriptive statistics describes what happened. Probability is about what could happen, and it's the foundation that makes the rest of statistics legally possible. Probability is the measure of how likely an event is, on a scale from 0 to 1. 0 means impossible. 1 means certain. Anything in between is where life actually happens. The sample space is every possible outcome. If you flip a coin, the sample space is heads and tails. An event is any subset of the sample space. Getting heads is an event. Basic probability rules. The probability of something happening plus the probability of it not happening equals 1, always. If there's a 30% chance of rain, there's a 70% chance of no rain. This is called the complement rule, and it's the least surprising thing in statistics, addition rule. Probability of A or B equals probability of A plus probability of B minus the probability of both. You subtract the overlap because otherwise you counted it twice. If A and B can't happen simultaneously, they're mutually exclusive and the overlap is 0. Simple multiplication rule. Probability of A and B equals probability of A times probability of B given A already happened. That given A happened part is conditional probability. And it's where things get interesting. Conditional probability, P of B given A, is the probability of B knowing that A already occurred. This shrinks your sample space. You're no longer asking what could happen in general. You're asking what could happen in this specific situation where A is already true. From this comes one of the most important and most misunderstood results in all of probability, Bayes' theorem. P of A given B equals P of B given A times P of A divided by P of B in English. You have some belief about the world, a prior. You observe new evidence. You update your belief based on how likely that evidence was under different scenarios. The result is a posterior probability, a smarter, updated belief. This sounds abstract until you realize it's how doctors interpret test results, how spam filters learn, how courts should evaluate forensic evidence but often don't. Bayes' theorem is not just math. It's a philosophy of rational belief update. Misunderstanding, it leads to what's called the prosecutor's fallacy, confusing P of evidence given innocent with P of innocent given evidence. People have gone to prison because of this mistake. Statistics is not a spectator sport. Independence. Two events are independent if knowing one happened tells you nothing about the other. Coin flip 1 and coin flip 2. Completely unrelated. If they're not independent, they're dependent, and you need to account for that ROM variables, bridge probability, and data. A random variable is a variable whose value is determined by a random process. Discrete random variables take countable values, number of heads in 10 flips. Continuous random variables take any value in a range, the exact time until something happens. Each comes with a probability distribution, a description of how likely each outcome is. For discrete, the binomial distribution models the number of successes in a fixed number of independent trials, each with the same probability of success. Flipping a coin 10 times and counting heads. The Poisson distribution models the number of events occurring in a fixed interval when events happen independently at a constant average rate. Number of emails per hour. Number of customers per minute. Rare events in large samples. For continuous, the uniform distribution, all values equally likely. The exponential distribution, time between events. And then, the big one, the normal distribution, the bell curve. Symmetric, centered at the mean, spread determined by standard deviation. It shows up everywhere in nature. Heights, measurement errors, test scores. The reason it appears everywhere is the central limit theorem, possibly the most important theorem in all of statistics. It says that regardless of the population distribution, if you take large enough samples and calculate their means, those sample means will be approximately normally distributed. Always. This is why you can apply normal-based methods to all sorts of messy real-world data. This is why statistics works at all. You've described your data. You understand probability. Now comes the actual goal. Making conclusions about a large population using only a sample, because you can't measure everyone. You measure some people and extrapolate. This is inferential statistics, and it requires you to be honest about uncertainty. Sampling. A population is every subject you care about. A sample is the subset you actually measured. Good samples are representative. They look like the population in all the ways that matter. Bad samples are biased, systematically different from the population in ways that mess up your conclusions. Simple random sampling. Every member has equal chance of being selected. Stratified sampling. Divide population into groups, sample from each group. Cluster sampling. Divide into clusters, randomly select entire clusters. Systematic sampling. Every nth person. Each has trade-offs in cost, feasibility, and potential for bias. Estimation. You take a sample, calculate a statistic, say, the sample mean, and use it to estimate the population parameter, the true mean. The sample mean is called a point estimate. It's your best single guess. It's almost certainly wrong, but hopefully close. To express uncertainty, you build a confidence interval. A 95% confidence interval means if you repeated this sampling process a huge number of times, 95% of the intervals you constructed would contain the true population parameter. This does not mean there's a 95% chance the true value is in this specific interval. The true value either is or isn't in the interval. The 95% is about the procedure, not this particular result. Almost everyone misinterprets this. Now you don't. The width of a confidence interval depends on two things. Sample size, bigger sample, narrower interval, more precision. And confidence level, higher confidence, wider interval, less precision. There's always a trade-off. Want to be more certain? Accept a wider range. Want a narrow range? accept more uncertainty, or collect more data. Nothing is free. Hypothesis testing. This is the machine at the center of modern science. You have a question, you set two competing claims. The null hypothesis, H0, is the boring default. Usually, no effect, no difference. Nothing interesting is happening. The alternative hypothesis, H1, is what you're actually trying to demonstrate. Something changed, something differs, something is happening. You then ask, if the null hypothesis were true, how likely would it be to observe data as extreme as what you actually got? That probability is the p-value, small p-value. Below your threshold, typically 0. ZO5 means your data would be very unlikely if the null hypothesis were true. You reject the null hypothesis. You declare a statistically significant result. You cautiously suggest something might actually be going on. Large p-value, you fail to reject the null. Not the same as proving the null is true. You just don't have enough evidence against it. This distinction matters enormously and is routinely ignored. The threshold, called alpha, is your significance level. Set it before you look at the data, not after. Setting it after is called p-hacking, and it's why a disturbing fraction of published research findings don't replicate. Type I error, rejecting the null when it's actually true. False positive. You said something is happening when it isn't. Probability of this equals alpha type 2 error, failing to reject the null when it's actually false. False negative. Something is happening but you missed it. Probability of this is called beta. Power is 1 minus beta. It's the probability of correctly detecting an effect when it exists. Higher power is better. You increase power by increasing sample size, increasing effect size, or raising your alpha threshold. All trade-offs. The most common hypothesis test is the t-test. One sample t-test. Is this sample mean different from a claimed population value? Independent samples t-test. Are these two groups different from each other? Paired t-test. Did this group change after some intervention? The t-test uses the t-distribution, which looks like the normal distribution, but with heavier tails, accounting for the extra uncertainty that comes from estimating the population standard deviation from your sample. The chi-square test tests relationships between categorical variables. Are these two categories independent, or are they associated? You compare what you observe to what you'd expect if there were no relationship. ANOVA, analysis of variance, tests whether 3 or more group means are different from each other, because running multiple t-tests inflates your type I error rate. Every extra test is another roll of the dice. ANOVA does it all in one go. Now you want to understand not just whether things are different, but how things are related. Enter regression. Correlation measures the strength and direction of a linear relationship between two continuous variables. The Pearson correlation coefficient, R, ranges from -1 to 1. -1 is a perfect negative relationship. 1 is a perfect positive relationship. 0 is no linear relationship. Correlation does not imply causation. This is the most repeated sentence in statistics. Memorize it. Tattoo it somewhere. Because forgetting it has fueled countless bad headlines, flawed policies, and expensive mistakes. Sybil linear regression takes this further. You model the relationship between one predictor variable x and one outcome variable y. The result is a line, y equals beta 0 plus beta 1 times x plus error. Beta 0 is the intercept, value of y when x is 0. Beta 1 is the slope, how much y changes for a 1-unit increase in x. You estimate these parameters using ordinary least squares, minimizing the sum of squared differences between your predicted values and actual values. But how good is your model? R squared, the coefficient of determination, tells you what proportion of the variation in y is explained by x. R squared of 0.8 means 80% of the variability in your outcome is accounted for by your predictor. The remaining 20% is whatever you didn't include. Also known as life being complicated, multiple linear regression adds more predictors. Y equals beta 0 plus beta 1x1 plus beta 2x2 and so on. Now you're controlling for multiple variables simultaneously, holding everything else constant. What is the relationship between this predictor and the outcome? This is how you start to untangle messy real-world relationships where everything is correlated with everything else. But linear regression has assumptions. Linearity, the relationship between predictors and outcome, is actually linear. Independence, observations don't influence each other. Homoscedasticity, the variance of errors is constant across all levels of predictors. Normality, errors are normally distributed. Violate these and your estimates, standard errors, and p-values all become unreliable. Checking assumptions isn't optional homework. It's the difference between valid analysis and expensive nonsense. Logistic regression handles binary outcomes. Yes or no, success or failure. survived or didn't. You can't use linear regression when the outcome is binary. It'll predict probabilities below 0 and above 1, which is physically impossible. Logistic regression models the log odds of the outcome as a linear function of predictors, then transforms everything back to a probability between 0 and 1 using the logistic function. Outputs are interpreted as odds ratios, used everywhere in medicine, epidemiology, and credit scoring. You've been using distributions. Now you understand them more deeply. The sampling distribution of a statistic, like the sample mean, describes how that statistic varies across repeated samples. This is not the distribution of your data. It's the distribution of your estimates. Narrower sampling distribution means more precise estimates. Wider means more uncertainty. Standard error is the standard deviation of the sampling distribution. Standard error of the mean equals population standard deviation divided by the square root of n. Bigger sample, smaller standard error. Your estimates converge toward the truth as you collect more data. This is the central limit theorem working behind the scenes. Maximum likelihood estimation, MLE, is the method of finding parameter values that make the observed data most probable. Given this data, what parameter value would have been most likely to produce it? Maximize that. MLE has beautiful properties. Under general conditions, it's consistent, converges to truth as sample size grows. It's efficient, achieves the lowest possible variance among unbiased estimators. It's the workhorse of modern statistical estimation. Bayesian inference offers an alternative framework. Rather than asking what parameter maximizes likelihood of observed data, you start with a prior distribution over possible parameter values, representing your beliefs before seeing data. You observe data. You use Bayes' theorem to update to a posterior distribution, your updated beliefs given the data. The output is not a point estimate, but a full probability distribution. This feels philosophically satisfying to some people and infuriating to others. The debate between frequentist and Bayesian statistics is old, ongoing, and occasionally heated at academic conferences. Time series analysis, data collected over time, stock prices, temperature records, monthly sales figures. Time series data violates independence. Yesterday's value influences today's. You need special tools. Autocorrelation measures how correlated a series is with its own past values. ARIMA models, autoregressive integrated moving average. Model time series using past values, past errors, and differencing to achieve stationarity. Stationarity means the statistical properties of the series don't change over time. Most real-time series aren't stationary until you difference them, nonparametric methods. All those tests, t-test, ANOVA, correlation, assume something about the distribution of your data, usually normality. What if you can't assume that? What if your sample is tiny? You use nonparametric tests. Mann-Whitney U-test instead of independent samples t-test. Kruskal-Wallis test instead of one-way ANOVA. Spearman correlation instead of Pearson. These tests make fewer assumptions by using ranks instead of raw values. They're less powerful when normality holds, more trustworthy when it doesn't incremental design. Statistics isn't just analysis, it's planning. A poorly designed study cannot be rescued by clever analysis. The gold standard for establishing causation is the randomized controlled trial. Randomly assign subjects to treatment and control groups. Randomization balances both measured and unmeasured confounders. Blinding prevents placebo effects and measurement bias. Factorial designs test multiple factors simultaneously. Blocking reduces noise by grouping similar subjects. Design determines what questions your data can actually answer. Design before data collection, not after survival analysis. Time to event data. How long until a patient relapses? How long until a customer churns? How long until a machine fails? The complication. Censoring. Some subjects haven't experienced the event yet when you stop watching. Their data is incomplete, but still informative. You know they survived at least this long. The Kaplan-Meier estimator produces survival curves accounting for censoring. The Cox proportional hazards model estimates how predictors affect the hazard, the instantaneous risk of the event occurring at each point in time, multivariate statistics. Multiple variables simultaneously. Principal component analysis, PCA, reduces dimensionality. You have 50 correlated variables. PCA transforms them into a smaller set of uncorrelated components that capture most of the variation. You've gone from 50 dimensions to 5 without losing much information. This enables visualization, reduces computational burden, and removes multicollinearity. Cluster analysis groups observations by similarity. Discriminant analysis classifies observations into predefined groups, statistical computing. Modern statistics is inseparable from computing. R and Python are your tools. You'll write code to clean data, because real data is messy, mislabeled, inconsistent, and incomplete. You'll simulate distributions. You'll implement bootstrap methods. Resample your data with replacement thousands of times to estimate uncertainty without assuming a distribution. You'll use cross-validation to evaluate predictive model performance honestly. Train on one subset, test on another, measure how well your model generalizes to data it hasn't seen. Overfitting is the enemy. A model that memorizes your training data and fails on new data is worthless regardless of how impressive its in-sample fit looks. Here's the part most degrees rush through. Statistics is not neutral. The choices you make, what to measure, how to sample, what model to fit, what threshold to use, how to present results, all carry assumptions, values, and consequences. P-value misuse has generated a replication crisis across psychology, medicine, and social science. Studies with P less than 0.5 got published. Studies that didn't fail to get published. Researchers ran multiple tests and reported only the significant ones. Effect sizes were tiny but statistically significant due to enormous sample sizes. Statistically significant and practically meaningful are not the same thing. A drug that reduces blood pressure by 0.2 millimeters of mercury can be statistically significant and medically irrelevant simultaneously. Confounding is the ghost-haunting observational studies. Ice cream sales correlate with drowning rates. Both increase in summer. Ice cream does not cause drowning. Summer causes both. A confounder is a variable associated with both predictor and outcome that creates a spurious apparent relationship. Randomization eliminates confounding. Observational studies must control for confounders statistically, but you can only control for confounders you know about and measured. Unknown confounders remain. This is why correlation does not imply causation, and why moving from association to causation requires extraordinary care. Simpson's paradox. A relationship present in several groups reverses when groups are combined. University admission data might show women accepted at higher rates than men in most individual departments, but lower overall because women applied to more competitive departments. The aggregate masks the truth. Always examine subgroups. Ethical data collection, informed consent, privacy, anonymization. Who owns the data? Who benefits from the analysis? Who might be harmed? Algorithmic systems trained on biased data reproduce and amplify those biases. Predictive policing, credit scoring, hiring algorithms. Statistics built the tools. Statisticians are responsible for understanding where those tools go. 4 years of statistics gives you the ability to look at uncertain, messy, complicated reality and extract signal from noise. You learn to quantify what you don't know, which is rarer and more valuable than it sounds. Most people are either falsely certain or completely lost when facing uncertainty. You become someone who can say exactly how uncertain you are, and why and what it would take to be less uncertain. You learn to design studies that actually answer the questions they're supposed to answer. To build models that generalize rather than memorize. To communicate results honestly, including the uncertainty, the assumptions, and the limitations, rather than overselling conclusions to make them sound cleaner than they are. The world runs on data. More of it every second. Most of it poorly analyzed, selectively reported, or dangerously misinterpreted. Statisticians are the people who know the difference. And right now, there are not nearly enough of them. If you got something useful from this, a like makes the algorithm gods notice. Subscribe if you want the next degree explained before your actual graduation. And if you want to argue about frequentism versus Bayes in the comments, be warned. I have opinions, I have time, and I am not afraid to use either.